Hi, everyone. We continue our forward with normalization topic. So let me quickly repeat what have been done last time. We've seen a decomposition of relations. So how to check that our decomposition is the main method of normalization. If we want to normalize something, then we need to split a single table, single relation into two, or maybe into multiple tables, in such a way that every concept belongs to only single tables, to only single relation. That's the main goal of normalization. Normal form or normal kind of table is such a table that keeps only single concept, not mixed concept, not intermixed concepts. So each and every fact is stored only in single record, in a single relation, in a single tuple, in a single relation. That's the main goal. So that goal is achieved by decomposition. But we may decompose relations differently in many different ways, and which of those ways are good, and which of those ways are bad. So to check appropriateness, or is this decomposition maybe good, maybe not so good, but at least it will not lose any data, and will not get new data after some operation with it. So two methods or two properties of good decomposition is that decomposition need to be lossless, and decomposition need to preserve dependencies. And the lossless decomposition is decomposition that being joined back if we decompose a table R into tables R1, R2, and so on and so on, and Rn. And then if we natural join them back into single table, all the records be in place and no new records will be added. That's the kind of that's the essence of lossless decomposition. And preservation of dependencies tell us that we need not better to preserve not better, we need to preserve all the dependencies from original relation. If original relation is covered by multiple functional dependencies, and each dependency may be checked only to by contents of single table. If I have dependencies of columns A, B, and C, and columns A, B in one relation and attribute C is in another, I can't check them. So I can't find just a definition of dependency. Dependency is defined over attributes of single relation. So I can't check that attributes depend one on another if these attributes belong to different relations. So that's an idea that we are not allowed to split attributes, to put attributes to different tables if they belong to at least one dependency. That's two ideas: how to decompose good, and lossless decomposition. Maybe check this property of losslessness may be checked by checking that common columns, common attributes in both new tables after decomposition are keys for corresponding tables. So if I decompose a table into R1 and R2, and R1 and R2 has the same some shared columns, common attributes, B in this case, then B is to be key for R1 and key for R2. So alpha, all the other columns need to depend on B, and gamma need to depend on B. So that's one way. And let's remember what happens if our decomposition is not lossless. And this way we decompose one table into two, And then when we join it back, we experience multiple new records that are not from original table, doesn't contain them. So that's a problem. And we don't want such a behavior. So we lost not data. Essentially, we have much more data. We don't lose anything. All our records are in place, but we have something new, and that means that we lost not records, but we lost what's lost is our information, some constraints, limitation. Essentially, this table is maybe filled with all the combinations of original tables, original of domains for columns, and that would not bring us anything new information on the domain. Essentially, the table that keeps only appropriate combination, and we know that Kemper go to Kowalski pub and drink pills there. Oh, and we know that Kemper don't go to anything else besides Instack and don't drink anything else. And here we see, oh, Kemper drinks this there and that there, and that's not the fact. Fact is, Kemper drinks pills in here and Hefeweizen in there. So we lost our information, not records, but our knowledge is what is lost in here. And second thing is preservation of dependencies. If dependencies are defined this way, let's say defined, then essence of the preservation is we need to have all the columns in every dependency be kept in a table. So due to first dependency, we may extract only 3 columns, zip, city, and region in distinct table. But due to second dependency, that means that we can't split, we can't remove any columns from our original table. And if we go to this, then this decomposition, it may be lossless, but it lost, what's lost is dependency. We can't check the second dependency. That's another problem. And you can see the situation. What does it mean that dependency is lost? Essentially, that in table after joining back, table may contain more data, like in lossless violation, in lossless rule violation, and we don't want to have in our rebuilt table any new data. The same thing, we lost information of appropriate pairing, appropriate combination of values in single tuple. So that's essentially, that's just two sides of the same idea. We want to decompose in such a way that when we recompose it back, we don't we have all the records, all the original records, and nothing new. So these two ideas of dependency preservation and lossless decomposition allows to be sure that our data is kept intact. And then we go to first normal form, and first normal form tell us that we are not allowed to put anything but atomic values in every column, and that lets upper table here contains lists in a field of children. Children is a list. This child and that child and that child, maybe one child for some pairs, and two children, and maybe 5 children, and so on. Instead, first normal form dictates that we need to have a column with atomic values, thinking that child is an atomic value, and then repeat keys and essentially put a child to, or make a child a key in this relation. Problems are different that connected with first normal form, and main problem is if I need to change value, and let's say it turns out that Joseph is put here by error, and so I need to remove it from this list and add to, let's say that Johann is a child of Joseph is child of Johann and Martha, but not Maria. That I need to change, and essentially it's just single update. I need to change mother for Joseph, and that single fact that that previously information data about mothership was put in our database incorrectly. So I need to change essentially just single thing. But if I have such a table, I need to change 2 records to reflect this change. I need to remove from this list and then add to that list. So atomic fact, simple single fact is reflected in 2 different records. That's not too good, as 2 updates may be broken. So I may change it here and don't change it there, or I may add Joseph to first record and somehow my process of 2 steps is broken in between those steps and my data become inconsistent. So Joseph may be added to first record and not being deleted from the second. So multiple different small problems. And yes, we now in many cases we prefer to use tables this way, keeping lists and even nested tables, but that's not first normal form. And if we have table in non-first normal form, there hardly can normalize it further. But in the common case, that's impossible. So first normal form is just the basis for future normalization, and for future normalization, for normalization to second, third, and fourth, and fifth, and sixth normal form, we need to have a solid basis, and that solid basis is to have every column being atomic. And second normal form tell us about complex keys. Complex keys are something that connects are keys that consist of multiple attributes or multiple columns. If I have single column key, single attribute key, second normal form is automatic. So second normal form is my table is in second normal form if and only if every non-key attribute is minimally dependent on every key. So that's not different keys. That's not stud ID and number and lecture number. And I have a table of student attends. So stud ID, number of lecture, name of student, semester of student, of current semester of student. And if I look at this table, then non-key attribute name belongs to student, not to lecture. So essentially, name of student depends on just partial key, on part of the key, and not of the whole key. So that's not minimal key. What does it mean? Minimally dependent. Key is a minimal for every non-key attribute. Every non-key attribute depends on the whole key, not on the part of it. That's a means of minimally dependent. And name of student depends not minimally. We may make key smaller and only stud ID to make a key of stud ID, and it's still be a key for name and for semester. So that table is not in second number form, and name and semester depends on stud ID. And we can draw it in different ways. And the problem is to copy information of student, to make multiple copies, and that's not about spending data space, spending disk space, but that's about problems with changing. If we change semester for a student, we need to go everywhere and everywhere in multiple records, change it. And it may happen that we've not succeeded. We may not succeed at this operation on multiple records. And essentially, that's just single fact that student moves to new semester from third to fourth, and current semester is another. And it's better to store it just in single place, but not in multiple records, and multiple records. That's the main thing normalization aims at. So insert anomalies, update anomalies, promotion of current up to another semester. If we might delete anomaly and then lost information on student, and student that didn't attend anything, we can't put information of student in this table. So solution is to decompose it. And that's the first place where we have decomposition to make our tables consistent with normal forms, or make our tables such that we may say that normal form, that this table conforms to second normal form. If we decompose original relation into a table, let's say attends, that keeps only numbers, pairs of that student go to this lecture, and the key is a complex. It consists of two columns. So that's the first thing. And the second table, second relation, is anything else. But we need to add a key to name and semester. So name depends on stud ID, semester depends on stud ID. And so we have a table of students with stud ID being a key. And in first relation, in a tense, a key is complex, stud ID and number and lecture number. And here we have stud ID and name and semester that depends on a key. And anyway, if we have single column key, then essentially our table, our relation, is in second normal form by default. So we don't need to even check anything. Second normal form is about minimal dependency on key. And that may happen, as we need to check it only for complex keys that consists of multiple attributes. So that's the second normal form. I skip. That's just a quick reminder of what's done on previous lecture. And the third normal form is about non-transitive dependencies, and that's different definition of third normal form. But basic definition is like this: that table is in the third normal form if and only if for every attribute, for every functional dependency, this function dependency is either trivial, so right side belongs to left side, column B belongs to alpha, then that's trivial, that every column depends on itself, at least itself, and in every combination, and in combination of this itself with other columns. That's just definition of functional dependency that brings nothing new. Second, B is part of a key, so we don't need to check it. Essentially, third normal form doesn't check columns that belongs to second, that belongs to other keys. So, and the last thing, and that's the left part, alpha, and alpha is a combination of columns, maybe a single column, a second set of columns, maybe one column, maybe two columns, maybe something. Left part of every functional dependency need to be a super key. So we don't allow for anything to be in left part, but super keys. So what does it mean that super key? That means that every column depends on alpha. So That's the definition. And the last thing is the main thing. And that means that I can't have a column, let's say C. I can't have a dependency C arrow D, and C is not a key of relation. So just two columns in a table depends one from another, and that means that essentially, if that's the second case, if some dependency doesn't conform to this condition, that means that left part, C column in this case, is a concept on its own, in its own right. So we need to extract it and put in a distinct table. So anything that depends on, that should be a key in this table or another. If that's not a key in this table, we need to extract it and create its own table, like not like. So if we see here, let's say zip and city and region depends on them, and the key for the whole table is person, personer, and room. So everything depends on them, and if I check this dependency, zip to city and region, I can see, oh, that's not trivial. Zip and city and region are different. City and region is in city doesn't belong to keys, so city doesn't belong to a key that define that everything else depends on. So I can't say that everything depends on city. From city and region, we have dependency to, let's say, area code, but let's say name doesn't depend on city. So city is not a key, second condition. And the last condition, left part, is a super key. Zip is a super key, so everything depends on zip. Oh no. So that dependency from zip to city and region, 3 columns need to be extracted and put to a distinct table of zip, city, and region, and make zip key there. So that's a decomposition. And we need to leave zip in, let's remember rules of decomposition. We not just extract few columns and remove them from source relation and move them to another node. That's not the case. We need to put everything that's dependent. City and region are removed, but the key, we need to have intersection between decomposed tables. We need to have something common. So we need to have some fields to join those 2 tables back. If we remove zip from source table, then we have nothing in common. We have no common attributes to join. So zip need to be still here, but zip, city, and region forms new table, and we move all the data there. We can check that if we have a table in third normal form, then it belongs to second normal form too. And the thing that we don't, and now something new. So something new for this lecture: synthesis algorithm. How to build a relation, how to decompose. An algorithm called synthesis, but that's essentially decomposition. That's just a name. As with synthesis, essentially we have just one database schema, and we try to synthesize new database schema on base of this original schema. We have just single relation, couple of functional dependencies, F, and result of synthesis algorithm is multiple relations, such that that's a lossless decomposition. They preserve dependencies, and all the tables, all the relations, all new relations are in third normal form. How to do this? We need to find minimal coverage, and minimal basis is a minimal coverage of functional dependencies. And let's return to this idea. And yes, what's a minimal basis or minimal minimal coverage of a set of functional dependencies. We may check the two sets of functional dependencies. F is our original set and some other set that we check that whether it's minimal or not. So two functional dependencies may be, we say that they are equivalent. We may call them equivalent if we try to get every attribute set, just subset of attributes, single attribute, two attributes, another pair of attributes, triple attributes, all the attributes. So we need to extract every attribute set, all the attribute sets from left part and the right part, and check that closures and closure for attribute set is built using algorithm of attribute closure building. So A plus, we follow all the functional dependencies and collect everything that we may reach transitively. So we need to get all the attribute sets from the left part and calculate closure applying these functions, these functional dependencies from the left side. And for, let's say, for attribute A, we have attribute closure of ABC. For attribute B, we have the closure of A, B, C, D, E, F. For attribute F, we have closure of F itself, so and so on. And calculate closures or evaluate, let's say, calculate closures for the right part. So we have two pairs of closures. We have attribute set, let's say AB. Closure here for AB is ABC, and here is ABC. Okay, move to next attribute set. Attribute set of ABC. Closure ABCD and closure AB. ABC. So this is different. If we can find different closures for the same attribute set, and closures are built on applying functional dependencies, and they are different here and there. So if we can find such an attribute set that have different closures, then we may say that these functional dependency sets are not equivalent. But if all the closures are the same, that means that essentially that functional dependency set are the same, are equivalent. And then that's a way of checking for equivalence. So FC is a basis if it's equivalent to original functional set, functional dependency set. And then we check that functional dependencies are minimal. So we can't remove anything from the left in every functional dependency, remove a column such that we not break this dependency. And we can't remove anything from the right. If each dependency consists of some keys to the left and some columns in left part and some columns in right part. And we can, if both column sets, both attribute sets are minimal, so we can't remove anything, then that functional dependency is minimal. So we make them minimal, trying to remove every column and checking for functional dependencies. And if we, on some step, we can't, all the functional dependencies are minimal on some removal process, on some step of that removal process. And then we just merge functional dependencies with the same left side. That's possible. We just merge right side for them, and that's it. And that's minimal basis. That's minimal coverage of a functional dependency set. So let's return to synthesis algorithm to build a correct third normal form schema for the database. We compute the minimal basis for our functional dependencies, and essentially this process of minimal basis computing, minimal basis calculation, is essentially we remove extra dependencies that essentially just to the same. So in every functional dependency set, we may have super keys, not minimal keys, but super keys, and we don't want them. if A is a key, so we know that AB is a key to, AC is a key to, and AB and D is a key to. We don't, and we may have such dependencies in our list, but we want to get rid of them. So that minimal basis algorithm essentially forms small or smallest possible set of functional dependencies that's equivalent to original set. And then we have that minimal thing, that minimal functional dependency set. And essentially we build a table for every functional dependency. Our first is all the columns from left part and the right part. And for another table, we took another functional dependency and create another table of all the columns from the left and from the right part. And yes, we say, or we assign alpha, left part, to be a key in this table. So minimal basis calculation is fundamental here. When we build a minimal basis, then essentially we build a set of tables, and each table is defined by every functional dependency define a distinct table, and by default, not by default, by minimal basis computing algorithm, we have that all the alphas, all the left part are different. We merge them. So in minimal basis computing, so we have different tables with different keys. So that's it. And in some cases, we may check that so if in in our original table we have some columns that's just a key of this table, we need to extract them and create additional, just single additional table that consists of all the columns for key of original table. So that's just additional table. If we already have such a table, so our key belongs to here and some columns, then we don't need to perform this step. That's essentially the whole table, like a tens table. A tens table has just two columns, student number and lecture number, and no functional dependencies. So for F is empty, minimal basis is empty. Looping through all the functional dependencies, we build no new tables. No tables will be created as no functional dependencies here. And then we look, okay, we have a key. We have a group of columns such that this group of columns is the key of our table. So we have two columns that our key consists of two columns, stud ID and NR, and we form a table of just two columns. And it looks like we don't need to change anything in this table. So that's just optional step if we have no dependencies, a single dependency that has a key of source table, original table, being left part of that dependency. Then we need to just keep our table. That's rule is about this. And then if we can find trivial tables or tables that are just subsets of one another. So I have a table of AB and another table of ABC. So why do I need to keep pairs of AB if I have ABCs? I need to drop AB, eliminate AB, and leave only bigger table. So table with bigger number of columns. So that's synthesis algorithm. And the main step is first to compute minimal basis, and then automatic step here, additional third step And another additional step, if I can see that I have tables that just repeat them, repeat bigger table, I need to remove a smaller table. So let's look at example. Big table for professor, multiple dependencies, and then if I perform normalization, minimal basis calculation, I can see that let's say room to personnel. I don't need this. I don't need this. Oh, let's street region city. Let's say zip and region city. Why don't I need to have? Will it belong to? Right. Let's return to. Let's return to minimal basis. Minimal basis. I need to minimalize all the left parts and all the right parts. And if I have dependencies with the same left and right side, I need to create. I need to remove functional dependencies that have empty right side and then union left side. Oh. So first dependency is minimal. I can't remove anything from the left, and I can't remove anything from the right. Everything depends on the left side. Second, I can't remove anything from the left. I can't remove anything from the right. Third, the same thing. So all the dependencies, that's a minimal coverage. That's a minimal basis. So I create a table for first dependencies. That's it, called professor. I create a table for room and person number. And then immediately I check this fourth step and I see that I need to eliminate a table if it exists bigger tables that can contain all the columns. So I have a table for room and person number. And I already have table with person number and room and something else. So I don't need to have that second table. I eliminate it immediately. I just created it and check, oh, I have a bigger table with the same columns. Third, I don't have street, region, city, and zip in professor table. So that's not covered by professor table. So I create new table, let's say zip codes for the third functional dependency. Then city, region, population, area code. That's not covered by anything else. That's minimal. I can't remove anything from left and right. So I create new table. That's it. Regional administration. That's not covered by anything, all other previous tables. And so I create table of region and administration. And that's minimal. And the last functional dependency, zip and region and city. Left part is already minimal, consists of single column, and right part is minimal, as I can't remove city from this dependency. Let's say city, and not lost this dependency. So city not present in other dependencies, so I need to keep it here. So zip, region, and city, and I might try to create a new table of zip, region, and city, and then I see here and see zip codes table, zip, region, and city. So this table is smaller, and I need to remove it, eliminate it. So I don't need, or I don't need to create it. So 4 tables is built on basis of 6 dependencies, and all the elimination happens due to the last step of algorithm, last condition. So result is here, and we may check everything, and then check that third normal form in every table. In every table, we have no transit, essentially dependencies on non-key attributes. What violates third normal form is dependencies of non-key attributes. Let's say name depends on person and air. Okay. Level depends on person air. Room depends on person air. And Personer depends on room, but they both are keys. Personer is one key and room is another key. And then so room doesn't depend on something that's not a key. And personer depends on room, and room is just another key. So that's okay. That dependency is okay. We don't want dependencies of non-key attributes from non-key attributes. Let's say city from street. But we don't have such dependencies here. All the dependencies are from personer and from room, and no dependencies between non-key attributes. Okay, zip code, street, region, city. Zip depends on all of them. Okay, and region and city depends on zip. So let's check street. Street belongs to a key, so we don't need to check anything. Region belongs to a key. City belongs to a key. Zip belongs to another key. So the whole table consists of every attribute, every column in this table is part of some key. So we don't need to check anything. If the whole table, every column in the table is a part of some key, then we have no non-key attribute. So we don't need to check anything, and such a table is automatically belongs to third normal form. So if we have no non-key attributes, so we can't have dependencies between them. So zip code consists of key columns, and that means that it's automatically in third normal form. Cities, city and region, population and area code, and we see here that population and area code is non-key attributes that don't belong to a key. Let's check. Population depends on the whole key. Area code depends on the whole key. Is their population to area code dependency or back? No, we don't have such a dependency in the list. So okay, great. So all the non-key attributes depends on the whole keys, and there are no transitive dependencies between non-key attributes. Great. Administration, single key here. Administration, non-key attribute depends on only on region. Great. So that's it. We may have some special situations, and let's look at, and yes, for third step. We have A, B, C, and D of table. That's just an example for some corner cases. A, B, C, and D, and B depends C and D, and D depends and B depends from D. So let's look here, and we understand what defines the whole table. So if I know B, then I know C and D, but A is unknown to me. And if I know D, then I know B, and transitively I know C, but A is unknown. So every column. So if that's a third rule. If I have some columns that don't belong to functional dependencies, that means that those columns should be parts of keys. So they are not that they don't depend on anything. So they should be parts of keys. Every column that don't belong to functional dependencies. So keys of R. Key is B. B defines C and D, but to define A key need to define everything. So to define everything, I need to have A in the right side. But to have A in the right side, I need to apply Armstrong axiom of augmentation and add A to the left side, and A to the right side, and A to the left side. And then I have complete dependency in such a way that right side contain all the columns. B may be added to the right side, so B depends on B. B defines B, C, D, and to define A, I need to add A to the left. And then I have complete functional dependency, and left side is a key, is a super key, due to the fact that all the columns are in the right part. That's definition of super key. Set of columns that define all the columns of relation. And I need to go to such a super key by augmentation rule, adding all the appropriate columns to right side and to left side. So first dependency converts to by augmentation to this, and then left side of it, AB is a key. The same thing for second rule. I may follow transitive dependencies and know that if B depends on D and C and D depends on B, then I can add C here. I can add D itself here to the right side, and to add A, I need to add it to left side too. So key is AD. That's an idea how to build keys in this case. And then I try to decompose it. First, I decompose first dependency. That leads to B, C, and D. And then I decompose to that's second step. I create a key of AB. So if I have a key for table, then I need to create a table that contains only these columns. And key are found by augmentation rule. So I need to find column sets that define everything else. And in this case, I can find two different keys using augmentation rule. And then I convert this to a table. DB is already in the first table. B and D is already here, so I don't need to create another table. And then I need to create tables for AB and AD. And if I create such a table for AB, then AD I don't need to create, as it will be cleaned. So a result of synthesis algorithm is this. First dependency, create this table, BCD, and to store key somewhere, to have a table that store a key, then I have a table of AB. And to find, let's say, a D, I need to search in a table of R2, and then find a B, and then go to R1. Let's check, and we've already done this, whether zip codes table, street, region, city, and zip is third normal form. It has two different keys. We check that all attributes are part of keys, so we have no functional dependencies that are violated, or evil functional dependencies. Functional dependencies that are violated. So we have no non-keys, attributes that are non-keys. So this decomposition follows third normal form due to this fact. Then check is this table preserve dependencies. First dependency, all the dependencies are here. So we have no dependencies that has something in zip codes and something in another table. So all dependencies are preserved. And for lossless, we build these zip codes from big professor relation, and we see, look here and see that in intersection of professor table and zip codes table is street, region, and city, and street, region, and city is is a key for this table. So yes, decomposition is lossless, and criteria of lemma is fulfilled due to criterion of lemma is that intersections of tables after decomposition, in this case intersection is this, street, region, and city, is a key in this table. So that's it. And we can check that synthesis algorithm preserve dependencies, and to check that algorithm preserve dependencies, we need to know that no dependencies will be split between tables. And yes, we have second step, that for every dependency, we'll have a table, we have a relation that consists all of them. So no dependencies will be distributed between different tables due to second step of synthesis algorithm. And that means that algorithm preserve dependencies. About losslessness, we need to check keys, and that's another step, and I'll leave it for your exercise. And then it creates relation in third normal form. So no keys, no, that we need to look at minimal basis and to second step too. So let you check it. And second normal form depends on third. So everything that's in third normal form depends is in second normal form automatically. So and synthesis algorithm produce only third normal form, nothing in smaller normal forms. And then let's look at it. If I have some result of the decomposition, some table that's a result of decomposition, Ri created on third step, built it from keys. So Ri contains a key of original table, and Ri contains no non-trivial FDs, so only trivial FDs and trivial functional dependencies. So no other columns. That's definition of step 3 in our synthesis algorithm. This table has no non-trivial, so only trivial. And trivial functional dependency is a dependency that left part and that right part is a subset of left. That's trivial. So key is a set of columns and nothing else. So if I have some non-key column here, then I have non-trivial dependency from this. This non-key depends on the whole key. So nothing, that means that nothing else in this table but a key. So if table created on third step contains a key, nothing else. So it contains a key, so no other columns, that's automatically in third normal form. So nothing, no columns to violate third normal form rules. And if a table created from a functional dependency, it consists of all the columns. Left part is a key of this table, and that key is a minimal due to minimal basis computation process. So that's minimal due to minimal basis computation. Essentially, do exactly this. It create minimal left parts and minimal right parts too. And alpha is a key, and by construction of this table, so alpha arrow to B, that's this dependency. This is here. Third, alpha to beta is not violate anything due to fact that alpha is a super key of this table, of this small table. So we have no violation of third normal form rules. And let's say we have another dependency, gamma to delta, other non-trivial dependency. So gamma to delta is not equal to alpha to beta. Alpha to beta is our functional dependency that we built upon, that we built our table upon. So due to minimal basis computation algorithm, delta need to belong to alpha due to right reduction, and gamma depends on alpha. And delta contains only attributes of a key. So as delta belongs to alpha, and delta belongs to alpha due to we remove anything else from the right part on the minimal basis calculation. So delta contains only attributes of a key. We know that alpha is a key and delta is a subset. So gamma to delta, no non-trivial functional dependencies, even if we have them here. No such dependency can be transitive, can be transitive. It can be evil as right part is attribute of a key. And by definition of third normal form, if right part B is an attribute of a key, that's good. So table is in certain normal form if one of possible conditions that right part is an attribute of one key. And here we have that our delta contains only attribute of a key, so that's a part of a key, and no functional dependency can violate third normal form of this kind. So synthesis produce third normal form, or everything that algorithm of synthesis produce is only third normal form relations. And this next normal form, third normal form, is have attention to. So what if we have multiple keys? Let's define Boy's code normal form and then compare it with third normal form. And Boy's code normal form was defined to refine properties of third, and at that time fourth normal form was already defined, so it called not fourth, as fourth is defined before, and Boy's code normal form is a refinement for the third normal form that was found or defined later, and that's why they call it this way. BCNF, Boy's code normal form. So table would be in Boy's code normal form if and only if for all the dependencies at least one condition holds. That dependency is trivial, like in third normal form, or alpha is a super key in the whole table. So the only difference is absence of the second rule. In third normal form, one condition of trivial dependency, super key, they are the same, and right part is an attribute of maybe some other key, attribute of at least one key. Third normal form allows for such tables, and Boy's code doesn't allow for tables where we have dependencies on other some columns that depends on other keys. So result, in any case, anything that we have in BCNF, any table that's in BCNF, automatically in third normal form. That's just more hard condition. Just one condition is absent, is removed from the list. So everything that that follows that doesn't violate these two conditions automatically doesn't violate conditions in third normal form and more. And result that any schema can be decomposed into and the difference between Boy's code and normal form, between Boy's code and third normal forms, that's a preservation of dependencies. So we don't try to preserve dependencies in Boy's code normal form, and that condition of that's removed from definition here in comparison with third normal form is essentially about dependencies preservation. So we don't preserve dependencies and need to build smaller tables due to this. So our tables built to fulfill BCNF conditions are smaller, not bigger than third normal. They are smaller, and these tables may not preserve dependencies. So let's see at examples. And but before going to examples, essentially BCNF, choosing between BCNF and third normal form, that's about correctness versus efficiency trade-off, and that's why we prefer third normal form to have more efficient tables. And efficient tables means that we have everything in single table, and we may check check all the dependencies here, and that's faster to extract data. In Boy's code, we split it in smaller tables and maybe in bigger number of smaller tables, and then we need to, that would be correct, but we need to rebuild our source table with smaller efficiency. So zip code table is not, zip codes belong to third normal form. We've checked it just a few minutes ago, but it doesn't belong to Boy's code normal form. Street, region, city to zip is okay, but let's look at region and city. Region belongs to alpha. Yes. Let's look to zip fill. Let's check all the attributes. Street belongs to a key. So we have alpha is a super key. So we'll have all the dependencies and check that the left part is a super key, or right part belongs to alpha. So for the second, left part is a super key, and that's correct. And right part, region, beta belongs to alpha. Region belongs to zip. No, it doesn't belong to zip. So left part doesn't contain, so that's not trivial dependency. And we have only two conditions. One condition is trivial dependency, right part belongs to left part, or left part is a super key. So second condition is okay, and first condition, zip is not a super key. So let's say street is not defined by zip. So we can't say that zip is super key for this table. And region doesn't belong to left side, and city doesn't belong to left side. What does it mean? We may have such a table, one street, another street, and another street, and regions and cities are the same. Region is the same in the same city and the same zip. So several times, essentially, in this table, essentially we store multiple times that so some cities have this just single zip code, and essentially we store multiple times that Emerald City has all the streets of it has the same zip code, and U Street has the same zip code, and S Street has the same zip code. So that's a redundancy, and if we want to change this zip code, let's say some zip code revolution happened, zip code change happened, and Emerald City is assigned new new code. So we need to change it and here and there and there and there. Why? So that's a problem. That's a problem of redundancy that Boy's code normal form solves. So how to solve it? That's just a problem here. We have another bunch of conditions, and we can see that some tables that are in third normal form doesn't violate these conditions. Some conditions, so they don't belong to this zip code. So how to heal it? How to change tables? Maybe decompose them. So result would be good from Boy's code normal form view. So that's a decomposition algorithm. Essentially quite simple. So we have single table, and we want to decompose it in multiple tables, such that all the tables form a lossless decomposition. All the tables are each table in Boy's code normal form, and we don't look for dependencies preservation. So we don't need to check it. So algorithm at this. We say that our original table would be in the result anyway. let's see, street, region, city, and zip, we have a complete functional dependency that consists of everything. All the columns are here. So we need to keep it. So original table is a result of decomposition. So that's not a decomposition. So to decompose, we have a big piece of something and then decompose it, make different pieces. But in Boy's code normal form decomposition, that's not the case. The whole thing, the whole table, the whole relation remains, and then we add new tables that extracted from it, but in addition to our original table. And we can see what should be put in these additional tables: zip to region and city. So that's we need to have a table that keep our data. So result consists of a table. Oh, sorry. A result consists of a table, and R1 if our result, why is Z? So how to do it? We search for evil dependencies, alpha to beta. So we go to this and find a dependency from zip to region and city. That's evil. That's that's conditions that violates conditions. So we have some dependency and create new table that consists of columns from this dependency, like in third normal form synthesis algorithm, and another table that's our original tables that we're trying to split, removing all the dependent columns, and then remove our source table from result and add two new tables. So we need to put not Z but result here instead of Z. So what's a way to decompose? We have big table, and then we find one new table consists of everything in one evil decomposition, and second part is here. So applying decomposition algorithm, extract zip, city, and region. Zip, city, and region is extracted, and then zip and street. So, and then we remove city and region from here, right part, and what remains, street and zip. So here it is. So decomposition is lossless in this way, and for each zip we have just single city due to second table, and if we need to change that zip, and for each street we have single zip. So to remove. So decomposition is lossless, and second dependency is not preserved by this decomposition. So essential idea of Boy's code normal form is to create distinct table, the same thing, distinct table for all the evil functional dependencies, and then remove right part of functional dependency from here. Let's see another example. We have table of cities. For city, we know which region it belongs. Administration, let's say that's mayor or a governor or someone who administer this city now or this region now. So we have same administrator for region, and population for the city. Functional dependencies. Population depends on city and region. Administrator depends on region, and each administrator defines a region. So we can't have the same governor or mayor in multiple regions. That's a way. And so that's essentially dependency one-to-one. Each region has its own governor, and each governor governs only a single region. So table may look like this, that different, and Aachen is not and yes, North Rhine. So different cities in the same region with the same administrator and different population. So population depends on city, and it may happen that this city with the same name is in different regions. So population depends on city and region. And this table have key of city and region due to possible duplication of city name in different regions. So key this. So how to decompose it? How to decompose it? We see that for each city and region, we need to each columns look at functional dependencies: city, region, and population. Yeah, city, region, and population. So we need to have a table of city, region, and population. That's one table. And region and administration as another table. Looking at functional dependencies, we may think of this. So administrator belongs to region, and region belongs to administrator. So we need to have single table with NRW and Rutgers and Rutgers in another table. So formally, we look at cities table and check conditions: city and region to population. City and region to population. That's okay. So this functional dependency is not evil. Right, left side is a key, is a super key. That's okay. So we have two conditions to check. One condition is this left part is a super key, and second condition, right part belongs to left part. So city, region to population, left part is a super key. Administration to region. Region doesn't belong to this set, and administration is not a super key. So that's evil. Region is not a super key, and administration is not part of region set. That's evil too. So step to split this table into one that has region administration pair, and key would be it will have two keys. Region is a key, and administration is another key. So everything is may be found using other column, and then we have city and region as a key here, population as a key here, and we need to remove something from the right part. And as region is a part of key, we don't need to and don't want to break our key. If we remove region in our cities table, we'll have no key. So we remove administration, and city and region remains here, and population remains here. So result is lossless, and city region key here, region is key here, and administration is another key here. So let's check region to this table, region to administration. Region is a key, great. Administration to region, administration is a key, great. City region to population is not here. City region to population, city and region is a key, okay. And so that's it. Just we need to check only functional dependencies. So we have lossless decomposition, and in this case, all the dependencies are preserved, are still preserved. So that's a way to decompose something. And then stop. So force normal form will be on the next, and the last normal form. Last normal forms will be on next lecture. Thank you.